The fine structure meets strong magnetic fields, a quantum physics journey. How does the fine structure constant shape the world of electrons in a magnetic storm? Well, let's find out. The picture you see here is considered an experiment for the Zeeman effect, in particular, the strong Zeeman effect or the strong field Zeeman effect. And what we see here is that these are the line spectra that we see when we measure a atom, in this case sodium doublet and a zinc sharp triplet. And what this effect tells us is that when in the influence of an external magnetic field, we get splitting in the spectra. And hence the field off has a doublet and field off has a triplet. But when the field is on, we see that we get splitting in the energy spectra. And that's pretty darn cool. So, how do these relate with the fine structure constant? Well, let's take a look. So, the problem that we have here today is starting with the equation 7.84 and using equations that we see listed here, derive equation 7.86. All right, so that's a whole lot of nothing. So, let's see what these equations are. The goal is to end up at 7.86, which is the fine structure correction. You see that one up there, so we know it's first order. And we see that we get a formula here that relates to the magnetic orbital momentum number and the magnetic spin number, as well as the orbital angular momentum number, L. So we see we got quite a bit going on. Not to mention our friend, the principal quantum number, N. Okay? And to get to this, we have to treat the fine structure as the perturbation in the strong field. Okay? Because in the strong field, the Zeeman effect dominates, so the fine structure looks like the perturbation. And so remember that in the first order non-degenerate theory, the first order correction was the expectation value. So we're going to have the relativistic correction and the spin orbit coupling correction because both of them combined make the fine structure correction. And here we see the eigenvalue for the relativistic correction and we see the Hamiltonian for spin orbit. And of course, we're going to need equations 66 and 85, both of these to assess what's going on here in the Hamiltonian. Okay, so again, why is this important? Well, this provides the direct evidence of the quantization of angular momentum in atoms and the existence of electron spin, much like we talked about last time. So, like last time, what other effects does this allow us to measure? Okay, so this one's pretty algebraically intensive, although most of it is in the video, but if you want the PDF just for your collection, feel free to grab that using the link below. It is accessible to all members, so go ahead and get that. It's free to join. If you find value in this content, you can have a direct impact on its success by liking, subscribing, sharing with a friend, or donating through Buy Me a Coffee. No account required. So without further ado, let's dive into stop number 1. Alright, so clearly, we have a lot moving on here, and we have to be aware of a couple things. Also, remember again that this is the first order. Okay, so we can get into higher orders if we need to, but for this particular problem, we don't. So if we start by equation 7.84 like we're told, and we realize that the first order is just the expectation value, we see we have the expectation value of the perturbation. Again, if the B external is much greater than the B internal, or the magnetic field outside of the atom, the Zeeman effect dominates and we take the unperturbed Hamiltonian to be the Hamiltonian of the Bohr, so the Bohr energy levels, and add that with the Zeeman effect. And thus the perturbation has to be the fine structure that we see here. So by using linearity, we can split this expectation value up into two things. And what we see here is that for the spin orbit coupling and the relativistic corrections, we can use the following equations to substitute in. Again, all of the equations are on the first slide, so feel free to check them out. But from that, it's pretty easy to simplify down, at least this first part. Clearly, we have the eigenvalues of the Hamiltonian, which give us the energies, so we're fine. But this spin orbit coupling, we're going to have to be a little more careful. We have a lot of constants here, so let's bring them outside. And we realize that we have two things here that need to be manipulated with. The 1 over r cubed and the s times L. So let's see how we do that. With that, we see that we don't do anything with the relativistics just yet, but we can see that based on equation 7.66 for the 1 over r cubed and 7.85 for the s dot l, we see we get their eigenvalues and their integral expectation, so we're fine there. So all that together is the spin-orbit coupling that we need in the expectation value. Okay, so that brings us to stop one's completion, where we found the equation for the fine structure, but it's just not in terms of the fine structure constant alpha. And that is the primary goal of this whole exercise. How do we write this whole thing in terms of alpha? Well, we're lucky because from problem 7.14, we actually solved for what the Bohr energies were in terms of the fine structure constant, and we saw that we got alpha squared over mc squared over 2n squared. So we're fine there. But we also know that the Bohr energies have the form of negative E1 over n squared. So we're going to have to utilize both of these. And in doing so, what we see is that we get the 13.6 eV that we're used to seeing times 2 over mc squared because we solved this set of equations for, or these two expressions for alpha. And this, both of them will be substituted in at different times, so just bear with us as we go through this. But nonetheless, let the algebraic journey begin. Alright, so first off, we saw how the relativistic correction gave us the En squared up top here. And we also saw that we had the Bohr radius down here from the 1 over r cubed expectation value. So we have to sub both of those in using the equation and problem given. And from that, we just have a whole laundry list of algebraic simplifications. If we were to square every term in here, we got a negative and a negative, so that gives us a positive, so this negative remains unchanged, as we see here. And if we square every term that we see in the parentheses, we get this expression here. The reason to expand it like this is so you see that the mc squared cancels top and bottom, so we're fine there. Now over here for the Bohr radius, when we plug in h bar over the fine structure times mc, we get a cube on all terms. So we see that the h bar cubed cancels with both terms of the h bar squared up top. So we get rid of that. We also see that the mc squared over here from the constants of the spin-orbit coupling cancel with them down here. So what we're left with overall is the alpha cubed, an h bar down below, and an mc that comes up because when dividing by a fraction, same as multiplying by the reciprocal. Now, a little bit of hindsight here tells us that if we multiply this fraction by 1 and put a c over c there just to force the completion for a substitution, we'll see that this is actually the fine structure constant again. And we want to do that so that we can get everything away. In the meantime, we see the things highlighted in red can be factored out to some extent. So the alpha cubed here and the n cubed here, alpha to the fourth, n to the fourth, we can factor out an alpha squared and n cubed out of both of them. So that leaves an alpha squared here, one factor of n, one factor of alpha here, and you see that by pushing the c over c in, we have this purple expression, which probably by now you realize is just going to be the fine structure constant. And then we could use the second part of the equation from 7.14 and simplify this down to the form we need. So, with that, we make the substitution for alpha. So we have an alpha squared here, alpha times alpha, that's going to give us an alpha squared here. Highlighting both of them, we see that we can plug in for the alpha squared with respect to the 13.6 EV. Okay, of course, both of them come with a 2, mc squared to follow along. The 2 cancels with the 2 in the denominator, mc squared, 1/2, and 2 up top, they cancel, mc squared here, cancel, and this is pretty much done. The rest is just finding a common denominator with the spin-orbit coupling, and then we'll be good to go. Oh, yep, that's the second part of the 7.14, as mentioned. Okay, so clearly both of those terms from the relativistic and spin orbit coupling had a 13.6 on it, so we factor that out. And now we clearly see that we just need to distribute the negative 1 over 4n into both terms in the blue bracket. Wonderful. We see we get a cancel, cancel, and then we just get a plus double negative, 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 turns to a positive, times 3. We leave this alone for now. This one right here, again, I can multiply by the multiplicative identity, and it doesn't change anything. But I do this because clearly L plus 1 half, L plus 1 half, I see I'm going to need to find a common denominator between these two things. Hence the L times L plus 1 in the numerator and denominator. So now I can force that common denominator and simplify. Let us also note now that this plus sign can be written as a negative and a negative, and we do that for the obvious reasons of factoring the negative out. So let's see what can be done with that. All right, common denominator found. We add the numerators, and in this case, after factoring the negative, that becomes L times L plus 1 minus ML times MS. Of course, divided by a whole sloosh of L's. Okay, now there was a note in the book about, well, clearly this term here will go to 0 if L is 0, or rather, it would be considered indeterminate. So to cover the basis there, we have to be careful, and in that case, we reference J. Okay, so be aware the correct value in this case for L equals 0 is 1, and we see that in a later problem, but clearly if you speculated that the L being 0 here would be a problem, you're right, and we just have to force feed that. So nonetheless, we get the energy correction, which is the fine structure in this case, for everything in terms of the fine structure constant. Not much of a hard problem, but definitely a lot of meticulous maneuvering with the algebra. So just be aware, you're pulling from a lot of different places. So again, I like keeping all the necessities up front from what I need, and that way I can maneuver with them knowing the pieces I need to solve the problem. All right, so in summary, we covered, quite a bit. It was a little front loaded with all the stuff going on, all my talking points in my head. But once we got to the problem, it was pretty smooth sailing, thankfully. Not much trickery here. That being said, a massive thank you goes out to all my supporters for making this possible. I'm extremely grateful for your support. If you'd like to see more, you can also become a patron for access to supplemental material, current and future projects, especially some of the coding questions that are in this book, and one-on-one help. New content is posted weekly to fuel your curiosity. Books, notes, and other reference materials are found below, and if you have any questions, please feel free to reach out. As always, thank you for watching, and until next time, stay curious.